A single quartz slab can cost more than $10,000, about the price of a Rolex watch. Yet this luxurious material begins as anonymous mineral grains buried beneath the earth, crushed and ground down until they seem almost worthless. To transform those loose particles into a seamless surface that looks as though it were carved from a solid block of stone, they must undergo a demanding transformation involving immense pressure, controlled heat, and a series of highly precise manufacturing stages. Even the slightest deviation can cause the entire slab to warp, crack, and be rejected as waste. Keep your eyes on the screen as Factron Process takes you inside this industrial production line to reveal how seemingly worthless stone particles are reborn as one of the most premium surfaces in modern construction. Quartz has accompanied humanity for thousands of years, shaped into jewelry and decorative objects by the ancient civilizations of Egypt, Greece, and Rome. Today, this age-old mineral appears in millions of homes, hotels, and shopping centers. Nearly 400 million square meters of finished material are produced every year, helping drive an industry worth around $30 billion. Quartz is not only part of modern construction, it also quietly keeps time. Inside a battery-powered watch, a tiny crystal vibrates tens of thousands of times per second when an electric current passes through it, creating a steady and reliable rhythm. But behind that beauty lies an almost invisible danger. Cutting and grinding engineered quartz can release ultrafine silica dust that penetrates deep into the lungs, causing irreversible silicosis and, in severe cases, death. Before it becomes a flat, polished slab, quartz remains locked inside dense rock layers and open-pit mines. Extracting it is not as simple as digging it out with an excavator, because the rock mass is still bonded together as an almost continuous body. For this reason, crawler-mounted drill rigs move along the quarry bench, boring a series of holes measuring roughly 110 to 229 millimeters in diameter. These holes are not placed at random. They are arranged in a carefully calculated pattern that directs the blast energy in the intended direction. When the explosives are detonated with extremely short delays between each row, the rock is not pulverized. Instead, it fractures just enough to separate from the ore body and collapse into the collection area. Once the dust settles, hydraulic excavators and wheel loaders begin gathering the broken material. A large wheel loader can lift around 11 tons of rock in a single pass, quickly filling Komatsu mining trucks with payload capacities of approximately 38 to 64 tons. From there, truckload after truckload carries the quartz away from the mining face and toward the receiving area. After leaving the receiving area, the large quartz rocks are still far too coarse to enter the mixing stage. A vibrating feeder first spreads the material into a steady flow and delivers it to the primary jaw crusher. Inside, one fixed jaw and one moving jaw repeatedly compress the rock, breaking it into smaller fragments. Pieces that meet the required size fall through, while oversized material remains trapped for further crushing. The material then passes through a secondary crusher, where it is reduced to particles only a few millimeters across. From there, the stream moves through a multi-deck vibrating screen that separates coarse grains, fine particles, and powder into different fractions. Finally, the processed quartz is cleaned, dried, and stored in separate silos, ready for the next stage. Leaving the classified silos, bags of fine quartz powder pass through an automated weighing system before being discharged into a massive industrial mixer. Here, the fine powder and other mineral components are blended under tightly controlled proportions: 93% mineral aggregate and no more than 7% polymer resin. The entire batch then enters a heavy-duty forced mixer lined with wear-resistant steel. Yet, no matter how tightly the particles are packed, they still remain millions of separate mineral grains. Metering pumps therefore begin feeding unsaturated polyester resin into the mixer. As it cures, the resin forms a cross-linked polymer network that locks the material together, reduces water absorption, and improves impact resistance. Large steel mixing blades then lift the material from the bottom, force the particles through one another, and fold the mass back toward the center. The blades may initially rotate at only 2 to 12 revolutions per minute, allowing the resin to penetrate without sending fine dust into the air. In less than 2 minutes, the speed gradually increases to break apart powder clumps and disperse the pigments evenly. With every rotation, the resin coats more of the quartz surface. Crushed glass and reflective particles may also be added to create greater visual depth. Mixing stops only when every particle is evenly wetted, with no dry powder pockets or concentrated color clusters remaining. Once the quartz and resin mixture has been fully blended, it is transferred to the slab forming area. Before the material reaches the mold, an automatic unwinding system lays down a black polymer film that completely covers the mold surface. This film keeps the underside of the slab cleaner and allows the finished product to be released more easily after pressing and curing. Before being spread into the mold, the quartz mixture passes through a homogenizing conveyor, where the material is laid into a thin layer and remixed one final time. The upper rollers do more than keep the material moving in the correct direction. They also break apart any remaining clusters, creating a more uniform and stable flow before slab formation. Once the mold is positioned, the quartz mixture is discharged from the hopper in precisely measured amounts, synchronized with the continuous movement of the mold below. Directly behind it, a mechanical screed moves back and forth in repeated cycles, leveling and distributing the material evenly across the entire surface. This precision is especially critical for ultra-thin slabs, because even a slightly underfilled area can later become a depression or a low-density zone after vibrocompression. Leaving the mixer, the quartz compound is spread into a thick layer across a mold that can measure up to 3.6 meters in length. But before it is compacted, this loose surface must pass through the Breton ROY automated veining center, where robotic arms begin breaking up the uniform base and creating sharp natural stone-like vein structures. The robot travels along a pre-programmed path across the entire length of the slab. Each time the tool head descends, metal blades penetrate the mixture and open channels with varying directions and widths. At the same time, fine nozzles inject a contrasting blend of fine quartz, polyester resin, and pigment into the newly formed grooves. This material fills the cuts and helps create the distinctive veining patterns that give each quartz slab its unique appearance. Once the mold filled with the quartz mixture enters the pressing chamber, massive steel doors close and seal the entire space. The vacuum system immediately activates, extracting the air trapped between the mineral particles. Even the smallest remaining air pockets can create internal voids and reduce the strength of the entire slab. Next, the vibrating table works together with an overhead hydraulic press, applying compressive pressure of approximately 2,000 to 3,000 psi. This force compacts the quartz and resin mixture until almost no empty space remains. The fully compressed slab is then transferred into a heating oven that may extend for dozens of meters. Depending on the resin formulation, some processes heat the slab at around 212 to 300 degrees Fahrenheit for 30 to 90 minutes. The heat triggers a cross-linking reaction, transforming the liquid polyester into a three-dimensional polymer network that locks the mineral particles firmly in place. Once the reaction is complete, the quartz slab leaves the oven and is cooled gradually to room temperature. Only then is the protective film removed, revealing a surface that has fully hardened and reached structural stability. After leaving the pressing and curing line, the quartz slab still carries a rough surface left by the compaction and vibration process. It is therefore transferred to a multi-head industrial grinding system, where diamond grinding discs rotate continuously at approximately 400 to 700 revolutions per minute. The first grinding heads remove the coarse outer layer, eliminating minor high spots and surface irregularities formed during pressing. Finer grinding stages then progressively level the entire slab, bringing it to a stable and uniform condition before polishing. The system then uses high-speed rotating pads, together with fine abrasive slurry, to produce the final finish. Depending on the design, the surface can be polished to a full gloss, reflecting light like premium natural stone or even glass. Once the surface has reached its final finish, the slab moves to the edge cutting area, where the product's final shape and dimensions are defined. Industrial diamond blades travel along the slab's perimeter, removing excess material left behind by the pressing and earlier machining stages. Rotating at high speed and driven by motors rated at approximately 10 to 20 kilowatts. These blades are powerful enough to cut slabs weighing hundreds of kilograms while maintaining a smooth and precise edge. During cutting, water is continuously sprayed onto the contact zone between the blade and the stone. This flow cools the cutting system and captures the ultrafine stone dust before it can become airborne. As a result, the cutting area remains almost free of drifting dust, with the contaminated water directed into a recovery system instead. The water carrying quartz particles is not discharged directly. It is routed to settling tanks, where the stone powder gradually separates from the water, then passes through a filter press before being returned to the cutting machines and grinding area. Through this recirculation loop, the factory can reduce wastewater discharge by approximately 90 to 95%. While limiting the release of silica particles into rivers, lakes, and groundwater. Stone sludge and trimmed edges are also collected for regrinding or use as aggregate, allowing both water and material to remain in circulation rather than becoming polluting waste. After cleaning, the slab enters the automated inspection area. Industrial cameras scan the entire surface to detect color defects, fine cracks, or internal voids that may have formed during pressing. At the same time, laser measuring systems check the slab's thickness and flatness across its full surface, ensuring that any deviation remains within extremely tight limits, typically only a few tenths of a millimeter. A multi-angle lighting system also examines the uniformity of the polished finish, helping identify localized dull spots, haze, or uneven gloss. Slabs that fail to meet the required standards are reclassified or sent for recycling, while those that pass inspection continue to the packaging and shipping stage. After leaving the finishing line, the quartz slabs are fully manufactured, but they are still not ready to leave the factory. First, they enter an automated marking system where each slab passes beneath a high-speed industrial printer. Within seconds, the machine prints a QR code, batch number, dimensions, and production data directly onto the slab's edge at a rate of approximately 6 to 10 slabs per minute. This unique identification allows the factory to trace each product back to its raw materials, production shift, and inspection records if a defect is discovered later in service. Next, the entire surface is covered with a transparent protective film, approximately 80 to 120 microns thick. This layer acts as a barrier against scratches, dirt, and friction throughout the journey. Slabs weighing hundreds of kilograms are positioned vertically on steel racks, spaced about 1.2 to 2 inches apart, with soft protective material placed around vulnerable edges to prevent impact damage. A fully loaded package can weigh between 4,000 and 6,000 pounds. The entire load must therefore be locked into timber or steel framing and secured with industrial straps capable of withstanding more than 2,200 pounds of tension. Only after a final stability check can the shipment be lifted onto a truck or into a container, ready to leave the factory and begin its journey to construction projects around the world. Once the quartz slabs arrive at a fabrication workshop or construction site, they begin an entirely new stage of their life cycle. First, technicians remeasure the installation area and transfer the data into the design software. On an industrial CNC table, the slab is firmly secured and cut precisely according to the digital drawings. Openings for sinks, cooktops, faucets, reception desks, and other architectural features are shaped using diamond tools or high-pressure water jets. The slab edges are then ground and shaped to match the required profile, ranging from smooth rounded curves to sharp beveled finishes. A sequence of progressively finer abrasives removes cutting marks and restores a polished edge that matches the main surface. Each finished component is measured again before being protected and transported to the installation site. The slabs are carefully lifted onto a prepared and leveled load-bearing frame, then secured with industrial silicone or epoxy adhesive. Finally, excess adhesive is removed, the joints are refinished, and the complete surface undergoes one last inspection. When every seam is aligned with precision, it nearly disappears, leaving behind a large continuous surface where an engineered material completes its journey and becomes part of the living space. From quartz locked deep inside the rock layers of an open pit mine to a polished countertop in a modern kitchen. Every slab must pass through a long journey shaped by mechanical force, chemical transformation, and near-perfect precision. It begins with drilling and controlled blasting to separate the rock from the ore body. The material is then crushed into several particle sizes, cleaned, dried, and blended with polymer resin and pigments. Robotic systems create veins that imitate the patterns of natural stone before the entire mixture is stripped of trapped air, compacted under intense pressure, and heated until millions of mineral particles are locked into one dense structure. The slab is then ground, polished, trimmed, inspected, and packaged before it can finally leave the factory. Even materials that appear as waste are returned to the process. Cooling water is filtered and recirculated. Grinding dust is collected, and trimmed stone edges can be crushed and reused as aggregate. What seems like a simple decorative surface is actually the result of massive machinery and tightly controlled parameters, where even a small deviation can determine the quality of the entire slab. Which stage of this journey impressed you the most? Share your answer in the comments, hit like, and subscribe to Factron Process to discover more extraordinary industrial production lines.